Before we do this next question, it's important to know that the direction of integration is really important. So if I'm normally differentiating from left to right like I do in green, the area above is positive and the area below is negative. However, if I'm integrating backwards or from right to left, like I have here in red, the area below is now positive and the area above is now negative. So it switches. So this is important to note for this next question. So example 4 says, well, this is a 2013 AP exam question. It says the figure shows the graph of f prime. So this is a derivative function shown to the right. The derivative f prime, the derivative of a twice differentiable function f. So that means the function is smooth and continuous, the derivative is smooth and continuous, and the second derivative is continuous. So it's on the closed interval from 0 to 8, and the graph of f prime has horizontal tangents at 1, 3, and 5. So I've kind of pointed them out in red. I'm just going to draw a little tangent slope. Okay, so we have a horizontal tangent here, here, and here. So the points of the areas of the regions between the graph of f prime and the x-axis are labeled. So we have those areas, those 4 different areas are all labeled as 2, 6, 3, and 7. The function is defined for all real numbers, and we have a starting value. And again, it's important because we're doing an accumulation function that we make note of the starting value at x equals 8, y equals 4. Part A says find all the values of x on the interval for which the function has the local min. So what we're looking for then is we're looking for where the graph crosses the x-axis. So I'm looking for where the graph crosses the x-axis, at here at 1. This coordinate here is going to be at 5. This coordinate here is going to be at 6. And those are the points which we have to check for local mins and maxes. So I'm going to mark that. That's going to be at 1, 5, and 6. Okay, so I have 0. My derivative is 0, so my slope of the f function is going to be 0 at that point. And I can check the slope value. So f prime to the left of 1 is above the x-axis, so it's positive, so it's going up. F prime to the right of 1 is also positive, so it's going to continue going up, so it looks like it's one of those slides. At 5, we have again a tangent. On the right of 5, we're going to go, it's below the x-axis, so we're going to have sloping down. At 6, we have our horizontal tangent. And to the right of 6, we see that the y coordinates of the f prime are positive, so we're going to be sloping up. Okay, so the local min is going to only be happening at x equals 6. So local min at x equals 6. So part B says determine the absolute min on the interval 0 to 8. Okay, so we're going to include the endpoints. When we talk about absolute min and maxes, we have to consider the critical points and also the endpoints. So we've been given the original position at x equals 8, y equals 4. So I've put that in my candidates list. Okay, so I'm going to have to compare coordinates in my candidates list to compare to see if I have an absolute min. So I put that in, that's my starting point. And I really only need to consider, now, although I could check my other points, I know that 5 is actually a local max. That would be something I could put in my candidates list. But really, I just need to consider for an absolute min, I have to consider the endpoints, and I also have to consider uh, the local min. So I'm going to put in 6 as my local min, and I have to work out that value. I also have to figure out what's happening at 0, because at 0, it looks like it's coming down, so it could potentially be another point of minimum. So I need to figure out two things. I need to figure out the F value at 6, and I'm going to find that out by my starting position of 4, and that is my starting point at x equals 8, and I'm going to integrate all the way to 6. Now, make note now I'm going from right to left. And so when I do that, I have to be careful because the area under the f prime then is going to be opposite. So f prime of t dt. So when I work this out, this is going to be 4 plus, now I have to work out my displacement based on the area from 8 to 6. So that area here is going to be this area in here. That has an area of 7, so that's going to be my displacement. Now, the difficulty here is that this displacement is above the x-axis, but because I am going in the opposite direction, I'm integrating in this direction here. That area is not positive 6, but the area of 7 is not going to be positive, but it's going to be negative. So I'm going to subtract 7. So when I get to that point, f of 6 looks like it's going to be -3. So I'm going to put that in my candidates list. So that's a potential absolute min. The other point I have to consider is f of 0. So f of 0, that's going to be equal to, maybe I'll choose a different color to do this one. So f of 0 is going to be equal to the starting point of 4, and that's going to start at 4 and x equals 8. Okay, so that's my starting point. I'm going to start from the right edge here at 8. I'm going to integrate backwards all the way to 0. And that's going to be under that f of t function. Okay, so looking at this, I'm going to have this area. It's going to be -7. So I'm just going to write this out. I'm going to keep track of this here. So f of 0, my starting point is 4, plus the area. This area, going from right to left, it went backwards 7, plus the area underneath here is going to be -3, but since I'm going backwards, my displacement is positive. So I'm going to do +3. The next area in here is above the x-axis. This area is positive, but since I'm going backwards, I'm going to use the opposite sign. So it's going to be plus -6. And then the area in this region here, getting all the way to 0, again, it's above the x-axis, but because I'm going backwards, I need to sign that as negative. Okay, so that represents the total displacement from 8 back to 0. Okay, so when I work this out, it becomes 4 plus that net displacement is going to be -15 plus 3, so it's going to be -12. So that value then, f of 0, is going to work out to be -8. Okay, so that's going to be -8. Then that indicates that that must be the absolute minimum. So this works out to be the absolute minimum. On C, it says, on what open interval contained in 0, 8 is a graph both concave down and increasing? So I'm just going to show the concavity on here. And concavity is going to be based on whether the derivative is sloping down or up. So the slope of the derivative would represent the second derivative. So for the first part here, from between 0, so my points are going to be from 0 to 1, that looks like it's sloping down. So it's going to be sloping down from here to here. Okay, so that's going to be a negative slope. So the second derivative is negative, so it's concave down. From 1 to 3, this region here is going to be sloping up. So it's going to be concave up in that region. So that's going to be from 1 to 3. And then from 3 all the way to 5, it's going to be sloping down. Again, that's negative concavity. And then from 5 all the way up to 5 to 8, that whole region is sloping up. So it's going to be positive concavity in there. And that's going to be all the way to the end point of 8. And we have inflections in there and 0 second derivatives in there as well. Okay, so the graph I want is concave down and increasing. Well, from 0 to 1, it's increasing and concave down. So that's going to be one region from 0 to 1. Okay, so I have both increasing and concave down. I have concave down from 3 to 5, and I have sloping down. It looks like it's sloping up from 1 to 5. Okay, so from 1 to 5, it's sloping up, but I only want the concave down portion. So from 0 to 5, so then the region that is concave down and increasing is going to be from 3 to 5. Okay, so at 3, that's our concave down boundary, and those are the two regions, the two intervals where it's both concave down and also increasing. Now, lastly, we have this function g of x. It's defined by the f of x cubed, so we're going to have to differentiate notation here because we want the slope of g at x equals 3. So that means I want to find g prime. Okay, so some function g is described with some embedded function f. We need to differentiate this implicitly, so I'm going to differentiate the outside, the cube. So we get 3 f of x squared, and then I go to the inside of that to get f prime of x. Okay, so I've differentiated the notation. I want to find the slope at at x equals 3. That means I need to find the f value at 3. So I need f of 3 times the derivative of f at 3. Okay, well, in this case here, we've been defined that f of 3 is going to be negative 5 over 2, so I could just replace that. So the only thing left to figure out is this f prime of 3. Well, f prime of 3 is the slope of the f graph, or the y value on the f prime graph at x equals 3. So in this case, we can see that f of 3 is going to be this coordinate here, at y equals 4. So f of 3 is equal to 4. F prime of 3 is equal to 4. I'm going to just plug that all in now. So g prime at 3 is equal to 3 times negative 5 over 2 squared. That's going to give us 25 over 4 times f prime at 3, which is 4. Working that all out, we end up with the 2 squared in the denominator and 4 cancel out. So we end up with 3 times 5 squared, and we get a slope of 75. So the slope of the line tangent to g at x equals 3, the slope is going to be 75.